So we've got 2 days to spend on related rates. And then on Wednesday, you guys will write your test on derivatives and applications of derivatives. So related rates, they involve being given the rate of change of one quantity and finding the rate of change of a related quantity. So this is different than the problems that we looked at earlier, where we weren't really finding the rate of change, we were finding the instantaneous. We were taking the derivative, okay? But also we were not given the information like we're going to be given here, where we're going to be given the rate of change of one quantity. We weren't given that before. Instead, we were asked to find the rate, let's say that the area of a circle was changing by when the radius was at a certain number. In this case, the radius is going to be changing. Okay, so that's going to be the difference between what we looked at before and this. So to do this, you need to determine an equation that relates the two quantities together and then differentiate both sides with respect to time. So that's the other difference, right? We didn't differentiate both sides. The left side always had a variable isolated. If it was y equals something, then we took the derivative and we said it was dy by d whatever the other variable was. Okay, but now you're going to differentiate both sides with respect to time. So when you take the derivative, there's always going to be something over dt, derivative with respect to time. So the radius r of a circular disk is increasing at a rate of 3 centimeters per second. So this is the first thing we're given, the rate of change of the radius with respect to time, because it's in centimeters per second. This per second part is the time. So in this case, we're given dr by dt, the rate of change of radius with respect to time, and that is 3 centimeters per second. We're asked to find the rate of change of its area. So you want to find dA by dr. That's what we're trying to find. I'm sorry, dr by dt. That's what we're trying to find. The rate of change of area at the moment when the radius is 4 centimeters. So that is what we're given and what we're trying to find. We want to find the rate of change of area, which will be dA by dt. We're given the rate of change of radius, which is dr by dt. And we want to find out what that rate of area change is at the moment when r equals 4 centimeters. So that's what we're given and what we're trying to find. Now, again, we need to have an equation or a formula that relates the area of the circle to its radius, which obviously is area equals pi r squared. And now you're going to differentiate both sides with respect to time. So when you differentiate a with respect to time, it'll be dA by dt. And on the right side, when you differentiate both sides with respect to time, we're going to be using the chain rule. So the 2 will come in front, so it'll be 2 pi r, but then we also have to multiply by the derivative of r with respect to time, which is dr by dt. We're using the chain rule on the right side, which means you're always doing it in 2 steps. You use the power rule first, and then you multiply by the derivative of what's inside the bracket. In this case, what's inside the bracket is just the variable r. And so its derivative is dr by dt, which we need because we're given that. That's one of the things that we're given. We're given dr by dt. So our equation has to involve that. We want to find dA by dt. Our equation has to involve that as well, and it does. And we're also given r, the radius. Our equation involves that. Okay, so now we can proceed to solve for dA by dt. It's going to be 2 times pi times r, the radius, which is 4 centimeters, times dr by dt, which is 3 centimeters per second, And so when you multiply the 3 and the 4, you'll get 12 times the 2 is 24 pi. And because you're also multiplying centimeters by centimeters, it'll be centimeters squared per second. So there's the exact value of the rate of change of area with respect to radius at the precise moment when the radius is 4 centimeters. Okay? So you see the difference between this and what we did before. Now the object is changing, and you're given the rate of change of one of the variables. You need to find the rate of change of the other. The radius of a sphere is increasing at a rate of 10 centimeters per minute. So that would be dr by dt, the rate of change of radius with respect to time, 10 centimeters per minute. Determine the rate of increase of the volume. So we want to find dv by dt. The rate of change of volume with respect to time is what we're trying to find at the moment when r, the radius, is 10 centimeters. So that is what we are given and what we are trying to find. So we need to have an equation that relates volume of a sphere to radius. And the formula for volume of a sphere does that. It's 4/3 pi r cubed. And just like we mentioned last week, any equations that you need for any of these problems on the test, you will be given the equations. So we've got our equation that relates radius to volume, and now we differentiate both sides with respect to time. So on the left, it'll be dv by dt. And on the right, when you use the chain rule, the first step is using the power rule. So the 3 comes in front, multiplies by the 4/3. The 3's will cancel. So you'll get 4 pi r squared. Remember, the power always decreases by 1. But then we're using the chain rule, so we also multiply by the derivative of r with respect to time, which is dr by dt. So there we go. We want to find dv by dt. We have everything else on the right side. It's 4 times pi times the radius, which is 10 centimeters, and that has to be squared, times dr by dt, which is 10 centimeters per minute. So when you square the 10, you'll get 100 centimeters squared, times the other 10 would be 1,000 centimeters squared, times the 4 is 4,000 pi centimeters cubed per minute. So there's the exact value of the rate of change of volume with respect to time at the moment when the radius is 10 centimeters. And obviously, if you wanted to know what that was, rounded to a certain number, then you would multiply the 4,000 by the pi. Okay? Number 3 says a 13-meter long ladder is resting against a wall, and the bottom of the ladder is being pulled out at a rate of 1 meter per second. How fast is the top of the ladder sliding down the wall at the moment when the bottom is 12 meters from the base? So for this one, let's draw a bit of a diagram. We've got a ladder leaning against a wall. So the hypotenuse of that triangle represents the ladder leaning against the wall. And the one thing that is constant here is the length of the ladder. That's going to be 13 meters. That will never change. But what is changing is the base of this triangle, because the ladder is being pulled away. The bottom of the ladder is being pulled away from the wall. So that means that if we label this X, that's changing. It's getting larger. And as that happens, the height of this triangle is decreasing because the height is determined from the distance from the ground or the floor up to the top of the ladder. And so as the bottom of the ladder is being pulled away, the distance to the top of the ladder is going to be changing. So let's say that we have those sides labeled as such. And again, that 13 meters is a constant. Now, the bottom of the ladder is being pulled out at a rate of 1 meter per second. So if x represents the distance at the bottom is from the base of the wall, then that means that dx by dt, the rate that x is changing with respect to time, will be 1 meter per second. We want to know how fast the top of the ladder is sliding down the wall, so that will be the rate of change of y with respect to time. dy by dt is what we're looking for at the moment when x is 12 meters. So because we've got the rate of change of x with respect to time, we want to find the rate of change of y with respect to time. We need to come up with an equation that relates these two together, and that equation would be Pythagorean theorem, because now we'll also involve the hypotenuse, which is a constant. So x squared plus y squared equals 13 squared. Again, the hypotenuse is a constant. It doesn't change. So we'll get x squared plus y squared equals 169. And now we're going to differentiate both sides with respect to time. Okay? And for those two terms on the left, again, we're going to use the chain rule, which is 2 steps. The first step is using the power rule. The exponent comes in front, but then you also multiply by the derivative of what's inside the brackets. In this case, the derivative of x with respect to time would be dx by dt, plus, when you differentiate y squared, again, you use the chain rule. Power rule first, times the derivative of what's inside the brackets, which would be dy by dt. On the right side, the derivative of a constant is 0. So after we differentiate with respect to time on both sides, that's what we have. So if you look at what we need an x variable, which we have, it's 12. dx by dt, we're given 1 meter per second. The second term, though, we want to find dy by dt, but we also need to know what y is. We need to know what y is at the moment when x is 12. So we can use Pythagorean theorem to find out what y is at the moment when x is 12, because again, the hypotenuse is a constant. So if we use Pythagorean theorem here it'll be a squared plus b squared equals c squared. It doesn't matter whether we say a is x or y, it doesn't matter. Let's just say it's x, so that'll be 12 squared plus y squared equals 13 squared. So y squared will be 13 squared, which is 169, minus 12 squared, which is 144. So therefore y squared equals 25, and y equals 5. So now we have everything that we need. Okay, we can definitely start plugging things in here. So we've got 2 times x, which is 12 meters, times dx by dt, which is 1 meter per second, plus 2 times y, which is 5 meters, times dy by dt, which is what we're trying to find. So that first term will be 2 times 12, which is 24, times 1, 24 meters times 1 meter per second. So I'll have 24 meters squared per second. And I can move that second term. Actually, let's just leave it there for now. 2 times 5 is 10 meters, dy by dt. And now if we continue up top, and I should have written equals 0 there. So now if we continue up top, we would subtract the 24 meters squared per second from both sides. So we have 10 meters dy by dt equaling negative 24 meters squared per second. And then we would divide both sides by 10 to get dy by dt by itself. So it would be negative 2.4 meters per second because we're dividing by 10 meters on the right. So there's the rate of change of y with respect to time, and it's negative because the distance or the height of y is getting smaller. As the bottom of the ladder is pulled away from the wall, the top of the ladder slides down. So the height is getting smaller at a rate of 2.4 meters per second. Okay? Number 4 says a ship A passes a buoy at 9 a.m. traveling north at 12 miles per hour. Ship B passes the same buoy at 10 a.m. heading east at 18 miles per hour. Find the rate at which the distance between the two ships is increasing at 11 a.m. So again, we're going to have something that resembles a right triangle. We've got one ship traveling north, the second trip traveling east. We want to find the rate of change for the distance between the two ships. So in this case, the hypotenuse is not a constant, right? The distance between the two ships is always increasing. So if we say that's x, the height is y, and let's say the hypotenuse is z in this case. Ship A passes the buoy at 9 a.m., traveling north at 12 miles per hour. So that will be dy by dt. And ship B passes the same buoy at 10 a.m. It's heading east at 18 miles per hour. So that'll be dx by dt. In this case, we want to know the rate at which the distance between the two ships is increasing at 11 a.m. So now we want to find dz by dt. Right? The hypotenuse is not a constant in this case. It's always changing. It's always getting bigger. So again, we need an equation, a formula that relates all three of these together, which once again would be Pythagorean theorem. And now you're going to differentiate each term with respect to time using the chain rule. All three terms are differentiated with respect to time. We don't have any constants here. So this tells us that we need a value for x, we need a value for y, and we need a value for z at 11 a.m. And so here's how we get those, all right? So ship A passes the buoy at 9 a.m., and therefore at 11 a.m. it's been traveling for 2 hours. It's traveling at 12 miles per hour for 2 hours, so y will equal 24 miles. Ship B passes the buoy at 10 a.m., so at 11 a.m. it's only traveled for 1 hour at 18 miles per hour, so x will be 18 miles. And now because we have x and y, we can find out what z is, which will be the actual distance between the two ships, but that's not what we're trying to find. We're trying to find the rate at which z is changing with respect to time. Okay, But to get that, we have to find out what z is. And again, we can do that using Pythagorean theorem. X squared plus y squared will equal z squared. We know that at 11 a.m. x is 18, y is 24. So we can calculate what z squared is and then z. 18 squared plus 24 squared is 900. And the square root of that is 30. So at the moment, or at 11 a.m., the two ships are exactly 30 miles apart. But again, we want to know the rate of change for the distance between the two ships. So we can now calculate that using this formula that we got after differentiating everything with respect to time. So we have 2 times x, which is 18 miles, times dx by dt, which is 18 miles per hour, plus 2 times y, which is 24 miles, times dy by dt, which is 12 miles per hour, and that equals 2 times z, which we have as 30 miles, times dz by dt. So we've got 2 times 18 squared, 648. And that'll be miles squared per hour, plus 2 times 24 times 12, which is 24 times 24. I think that's 576, if I remember correctly. Yep. 576 miles squared per hour equals, on the right, 2 times 30 would be 60 miles dz by dt. So I can add those two together on the left because they are like terms. 1,224 miles squared per hour equals 60 miles times dz by dt. And then we would divide both sides by the 60 miles to get dz by dt by itself. So divided by 60 is 20.4. And you divided miles squared per hour by miles, so that gives us miles per hour. That's what dz by dt is. That's the rate at which the distance between the two ships is increasing at 11 a.m. Okay? Number 5 says determine the rate at which the area of an equilateral triangle is decreasing when it is 8 centimeters on each side and the side lengths are decreasing at a rate of 1 centimeter per minute. So we have an equilateral triangle, which is a triangle where all 3 sides have the same length. So the sides are all 8 centimeters. We want to find the rate at which the area is decreasing. So we want to know what dA by dt is. when the side lengths, so if we say that the lengths of each side is x, we can use any variable we want here. So we want to know what we're given dx by dt. It's decreasing, so it'll be -1 centimeters per minute. Because it's decreasing, that makes it negative. So we need to have a formula that relates the area of a triangle to x, the length of the sides. And the formula for area of a triangle is base times height divided by 2. That will be the formula that we will use here, or 1/2 base times height. But we can only have one variable. So right now we have two variables in there. We have b the base and h the height. Okay? If you were to differentiate that, you'd have to use the product rule. You would also have a dB by dt factor, and you'd have a dH by dt factor. But we're not given any information about h, the height. Okay? B, the base of the triangle, will be x. Right? So we've got that. However, we don't have anything involving h, the height. We're not given anything about h. We're not given the rate of change of h with respect to time either. So we cannot have h in our equation when we go to differentiate, because we're not given any information about h. We're not asked to find any information about h. So that tells us then that we have to write h in terms of the same variable that b is written in, the base. And b, the base, will be x. That's the base of the triangle. Now it's changing, right? But our equation will involve x because we're given dx by dt. But we cannot have the variable h in there. So we need to do some work here to write h in terms of b, the base, or h in terms of x. That's what we need to do. So that side there represents h, the height of the triangle. Okay? So if I take one of the right triangles now that I have formed, I got one on the left, one on the right. I need to write h in terms of x. Because it was an equilateral triangle, when we drop this h down, it's going to be a perpendicular bisector of the base. So the actual base of, let's say, the triangle on the left, the right triangle on the left, will be x over 2, or half of x. Because when we drop that perpendicular line down, it will bisect the base, because it's an equilateral triangle. So now we can use Pythagorean theorem to write h in terms of x. So using Pythagorean theorem, it'll be x over 2 all squared plus h squared equals x squared. The hypotenuse is x. So this allows us to write h in terms of x. So we'll have x squared over 4 plus h squared equals x squared. We'll subtract the x squared on 4 from both sides, and we'll get h squared equals, so that term on the right will be 4x squared over 4, because we need a common denominator here, minus the 1x squared over 4. So h squared will equal 3x squared over 4. If you have 4 of something, you subtract 1, that leaves you with 3 of those things. In this case, 3x squared over 4. And then when you take the square root of both sides, you'll take the square root of the x squared to get x. The square root of 3 we'll write as root 3. And on the bottom, the square root of 4 is 2. So there's an expression for h in terms of x. And again, we must do this because our original formula for area is 1/2 the base times the height. The base is x, but h, we cannot leave it in as h because we're not given h, we're not asked to find h, we're not given dh by dt, nor are we asked to find it. So we have to eliminate h out of the equation. And so now we can say that area is 1/2 the base, which is x, times the height, which will be x root 3 over 4. Over 2, excuse me. We've written h in terms of x. So just to simplify things here, I'll multiply all this out. So I'll have x times x, which is x squared root 3, over 2 times 2, which is 4. So we can say that area equals root 3 over 4 x squared. So now I will differentiate both sides with respect to time. So dA by dt, when you bring the 2, the power on the x in front, it'll be 2 over 4, which will reduce to 1/2. So it'll be root 3 over 2x. And then you also have to multiply by the derivative of what's inside the brackets. The derivative of x with respect to time is dx by dt, which we're given. Okay, we are given that. Also, x, we're given that as well. That is 8, right? X is the base of the triangle. Or, I'm sorry, that was dx by dt. So I labeled this wrong. 8 is actually the rate of change. It's dx by dt. It's not. But when we want to find out what x is, in this case here, that would be 8. It is 8 centimeters on a side. Yeah, I'm sorry. So that was correct. It is 8 centimeters on a side. So that will be the value of x. So we could have written that here as well. X will equal 8 centimeters. Okay, so dA by dt is what we're looking for. It'll be root 3 over 2 times 8 centimeters times dx by dt, which is negative 1 centimeters per minute. So 8 divided by 2 is 4. So it'll be 4 root 3 times negative 1, which is negative 4 root 3. And you're multiplying centimeters by centimeters, so it'll be centimeters squared per minute. So there's the rate of change of area with respect to time at the moment when x is 8. And so you can see that I'm always writing them as exact values. On the test, if you're asked to write it as an approximate, you'll be told what to round it to. Otherwise, leave everything as exact values. All right, number 6. A cylindrical tank has a radius of 3 meters. It's being filled with fuel at a rate of 2 meters cubed per minute. Determine the rate at which the height of the fuel in the tank is rising. So we've got a cylindrical tank here. A cylinder is like a soup can. Only this isn't a soup can, it's a fuel tank. And we're told that r, the radius, is 3 meters, and that would be a constant. That's not changing. Doesn't matter what the height of the fuel in the tank is, the radius will be a constant. So r is 3 meters. So we're given that. R is 3 meters. We're also being given the rate of change of volume with respect to time, dV by dt. It's being filled at a rate of 2 meters cubed per minute. That is the rate of change of volume with respect to time. We want to know what dH by dt is. The rate of change of height with respect to time. That's what we're trying to find. So we need an equation that involves the volume of a cylinder that relates it to the height of the cylinder. And that formula is volume equals pi r squared h. It's the area of the base, which is a circle, times the height. So we're given dV by dt, so we need to keep volume in there. The radius is a constant, that's not a variable. And we've got the variable h on the right, which we want to find dH by dt, so we need to keep that variable there as well. We only have two variables here, and that is volume on the left and height on the right. Again, r is a constant. It's not changing, so it's not a variable. So we can put that value of r in before we differentiate. R, the radius, is 3 meters, and the radius must be squared. So 3 squared is 9, so volume will equal 9 pi times h. And that'll be in meters squared. So the meters squared is a unit. So now we'll differentiate both sides with respect to time. So it'll be dV by dt equals, so on the right, the h is the only variable, it's to the power 1. So it'll be 9 pi times dH by dt. Remember, when you differentiate h, you use a chain rule, which means using the power rule first, so the 1 comes in front of the h, but then the power decreases by 1, so it becomes 1h to the power 0. That's why there is no h here. But then you also multiply by the derivative of what's inside the brackets. That's where the dH by dt came from. So we're given dV by dt. It's 2 meters cubed. And I forgot to write the meters squared at the end there. But dV by dt is 2 meters cubed per minute. And that will equal 9 pi dH by dt meters squared. You want to get dH by dt by itself. So we will divide both sides by 9 pi meters squared. So on the left, you'll have 2 over 9 pi. Meters cubed is multiplied by meters squared, which gives us meters per minute. And that's what dH by dt will equal. 2 over 9 pi meters per minute. So again, it's important to note here that because the radius is not changing, we can put it into the equation before we differentiate. The radius is a constant. Doesn't matter how high the fuel gets in the tank, that radius will not change. And as we look at this next one, which will be the last one today, the radius will be changing. In this case, the tank is a cone, a conical shape. So the radius will change. It has a height of 5 meters and a diameter of 6 meters at the top, which means the radius is 3 meters. Water is being pumped into the tank at 1.6 meters cubed per minute. Find the rate at which the water level is rising at the moment when the water is 2 meters deep. So in this case here, we're given dV by dt, the rate of change of volume with respect to time, is 1.6 meters cubed per minute. We want to know the rate at which the water level is rising, so that's dH by dt is what we're trying to find. at the moment when h is 2 meters. So that's what we're given and what we're trying to find. So a formula that relates the volume of a cone to its height, and again, that is the formula for volume of a cone, which you would be given if you needed it for a test or a quiz. So that'll be volume equals 1/3 pi r squared h. So this formula has two variables in it on the right. It's got r, which is changing, and it's got h, which is also changing. But if we look at what we're given and what we're trying to find, we're given h. We want to find the rate of change of height with respect to time at the moment when h is 2 meters. So we're given h, and we want to find dh by dt. So we want to keep that in the equation before we differentiate. But we're not given r or dr by dt, and we're not asked to find either of those. So we need to get rid of that variable r in our equation before we differentiate. And we can write an expression for r actually in terms of h. And here's how. At the top of the cone, which has a height of 5 meters and a radius of 3 meters, well, no matter where you go up and down that cone, that ratio will stay the same. The ratio of r over h will be 3 over 5. That ratio will be the same. As the water level rises or falls, that ratio will stay constant. So this allows us to write r in terms of h. If you cross multiply, you will get 5r equals 3h. So therefore r will equal 3h over 5. So there's an expression for r in terms of h. And we will now put that in our equation. Now we can say volume equals 1/3 pi times r, which is 3h over 5, and that needs to be squared, times h. So if we simplify this, we will get 1/3 pi times 9h squared over 25 times h, or volume equals, well, actually, let's do it this way. So on top, we've got 1 times pi times 9h squared times h. So that'll be 9 pi h cubed over 3 times 5, which is 75. So if we leave it as 3 times 25, because we can now divide the 9 by the 3, so that'll give us 3 pi h cubed over 25. Or 3 pi over 25 h cubed. So there's an expression for volume in terms of only one variable. And we can only have one variable here because we want to find dH by dt, and we're given h. So now when we differentiate both sides with respect to time, it'll be dv by dt equals the 3 on the h comes in front and multiplies by the 3 on 25. That'll give us 9 on 25 pi. The power on h decreases by 1, which gives us h squared, and then we multiply by the derivative of h with respect to time, the derivative of what's inside the brackets. So dv by dt is 1.6 meters cubed per minute, and that equals 9 pi over 25 h, which is 2 meters that needs to be squared, times dh by dt. So 2 squared is 4, times 9 will be 36 pi. So that'll be 36 pi over 25 meters squared times dh by dt. And then we'll divide both sides by 36 pi over 25 meters squared. So when you divide by a fraction, it's the same as multiplying by a reciprocal. So it'll be 1.6 meters per minute, because you're also dividing meters cubed by meters squared. And we multiply by the reciprocal, which is 25 over 36 pi. And 1.6 times 25 is 40. So that'll be 40 over 36 pi meters per minute. And that can be reduced by dividing top and bottom by 4, which will give us 10 over 9 pi meters per minute. So there's the exact value of the rate of change of the height of the water in the tank with respect to time. dH by dt. So again, we're always leaving these as exact values. All right. So there's a worksheet there. I have written the answers in brackets for each of these, so you can check your work, what you should get. Okay, you're going to have to look up some of these formulas, some of them, right? But remember, on the test, which you guys are writing on Wednesday, if you need any formulas, they will be given to you. Okay, so there's questions on both sides. I will post the solutions to Google Classroom, the key, so you can check your answers to make sure you're doing things correctly. Remember, your test on Wednesday will involve derivatives and applications of. So we went through that quiz last week on derivatives. So you got to know how to do all those types of derivatives, rules for derivatives, the power rule, the product rule, the quotient rule, the chain rule. You won't be given any of those for your test, so you got to know them. But if you need any of these special formulas, you'll be given those. All right. So I'll post the solutions to the worksheet so you can check